Optimization of regression analysis by conducting parallel calculations. Abstract. The regression analysis of large datasets by parallelization is investigated in the work. Different approaches to parallel computing are proposed. The parallel method of gradient descent and stochastic gradient descent is performed using OpenMP and MPI technologies. The efficiency of the proposed parallel algorithm is analyzed. A number of numerical experiments were performed. Acceleration of 5 times was achieved using the 6-core architecture of a personal computer. By varying the number of threads and processor cores, the possibility of further optimization of the computational process is established. The problem of erroneous exchange is considered, which often has a negative effect on acceleration during parallelization using OpenMP. The advantages and disadvantages of using each of the technologies are analyzed. Without reducing the generality, the software product is developed in the work, which can be used in the regression analysis of big data processing in a wide range of economic problems. Introduction. When processing large amounts of information, a large number of calculations are implemented, which consumes significant resource and time of its processing. Moreover, the construction of systems that perform the necessary operation depends on the type of data received and describe each specific situation. Due to the variety of data that can simultaneously characterize the task, there is a problem of creating techniques that will universalize the processing of large amounts of information regardless of its type. As is known in the static modeling, regression analysis is a set of statistical processes for estimating the relationships between a dependent variable and one or more independent ones. The most common form of regression analysis is linear regression, when the researcher finds the line or more complex linear combination that is most appropriate for the data according to some particular mathematical criterion. Regression analysis is mainly used for two conceptually different purposes. First, such analysis is widely used for forecasting and prediction, where its use intersects with the fields of machine learning. Second, in some situations, regression analysis can be used to infer causal relationships between independent and dependent variables. Regression methods continue to be an area of active research. In recent decades, new methods of regression analysis have been developed, such as time series, increasing groups, non-parametric regression, and so on. Modern economics uses many methods to assess the impact of factors on the level of development, but a special place is occupied by correlation regression analysis. This type of analysis allows not only to assess the reality of the influence of factors, but also to determine the intensity and momentum of their impact on the effective indicator of regional development. Big data is a field that considers methods of analysis, systematic extraction of information, work with data sets that are too large or complex to be analyzed by traditional data processing software. There are problems when regression analysis needs to be performed on big data. Big data as a concept is becoming increasingly popular in the world. It is used in marketing research, in the analysis of world markets, sociological research, and even elections. Those large amounts of data can contain important information that requires efficient processing. It is usually performed using machine learning algorithms that study the available data. However, as a rule, such calculations require duration and complexity at the stage of learning or forecasting, which makes it impossible to use implementations of sequential algorithms, because they are unable to cope with the current data. Therefore, the aim of this work is to study the performance of regression analysis on large data sets by parallelization. Parallel approaches to increase processing speed are proposed. Theoretical basis. In general, the linear regression model is defined as where y dependent variable, x property vector independent variables, n number of independent variables, theta vector of linear regression coefficients. Hypothesis is a function that best describes the purpose of machine learning, where h from x is hypothesis. I will use the least squares method to estimate the unknown parameters. It takes as an estimate of the parameter values that minimize the sum of the squares of the residues for all observations. Thus, the cost function takes the form where m number of sample items, n number of properties. The next step is to minimize the cost function. There are two known methods, the normal equation or the gradient descent. Normal equation, where x matrix of values of independent variables y vector of values of the independent variable, theta vector of regression coefficients. The research of the gradient descent method and the possibility of its parallelization is carried out in the work. This method requires a large number of iterations but works well even with a significant amount of properties. The difficulty in parallelizing this method is that the algorithm is quite consistent. Each subsequent update of the coefficients depends on their previous values. Gradient descent algorithm. Theta J regression coefficient. Alpha learning step. M the number of elements in the dataset. H theta hypothesis. XII string in the dataset. Xj in I, j element in the I string of the dataset. Yi dependent variable. It is necessary to iterate to a certain stop condition while updating the coefficients theta j. Gradient descent has a non-optimization stochastic gradient descent. This optimization method is well suited for solving the problem because it coincides faster on a large amount of data, but the method is not always accurate enough. Similarly, as in a previous formula, it is necessary to iterate to a certain stop condition while updating the coefficients theta j. Therefore, in order to solve this problem, the gradient descent method and the stochastic gradient descent method were parallelized using OpenMP and MPI technologies. Regarding the choice of OpenMP technology, the advantages are: due to the idea of incremental parallelization, OpenMP is ideal for developers who want to quickly parallelize their computing programs with large parallel loops. The developer does not create a new parallel program, but simply consistently add OpenMP directives to the text of the program. At the same time, OpenMP is a fairly flexible mechanism that gives the developer great control over the behavior of the parallel program. It is assumed that the OpenMP program on a single processor platform can be used as a serial program, but there is no need to support serial and parallel versions. Formulation of the problem. The main task is to find the regression equation of the form. There is one dependent stator temperature and several independent variables. The current sample size, which is taken to solve the suppressed problem of finding the regression equation of 500,000 elements, and the number of properties 7. However, the sample size can be much larger and vary the number of properties from 1000 and more. Then, the usual sequential algorithm can be long or calculations will be too large to fit in RAM. This problem can be solved by parallelizing the regression equation search algorithm. Search results. The paper parallels the gradient descent algorithm and stochastic gradient descent using OpenMP technology. Stages of parallelization of the gradient descent algorithm. In the first stage, only the code fragment of the whole algorithm, which is responsible for multiplying the matrix X by the vector theta in the function of hypothesis H, is parallelized using the OpenMP directive. Then, the parallelization of the calculations required to find the result of the const function. That is the parallelization of the function of hypothesis, which is described in the first stage, and the parallelization of the error simulation operation for each element. Time spent on the second stage of the parallel gradient descent algorithm with different number of iterations and flows on a two-core processor is given in Table 1 and Table 2, and the visualization of the results is presented in Figure 1 and Figure 2. Table 1. The results of parallelization of the second stage using a two-core processor. Table 2. Efficiency and acceleration, second stage, two-core processor. Figure 1. Visualization of execution time and parallelization of the second stage, two-core processor. Figure 2. Acceleration obtained by parallelization of the second stage, two-core processor. Similar numerical experiments were performed when tested on a six-core processor. Sometimes significant benefits cannot be achieved through fault sharing. Simultaneous updates of individual items in the same cache line coming from different processors invalidate entire lines of the cache, although these updates are logically independent of each other. Each update of an individual cache line item marks the line is invalid. Other processors that access another item of the same line see the string marked as invalid. They have to get a newer copy of the string from memory or elsewhere, even if the item they accessed has not been changed. This is because cache coherence is maintained based on the cache line, not for individual elements. As a result, there will be an increase in the relationship between traffic and overhead costs. Also, while the cache line is being updated, access to item in the line is denied. This situation is called false exchange. If this happens often, the performance of scalability of OpenMP will be significantly affected. Therefore, it is necessary to use various ways of the distribution of iterations. At this stage, the parallelization described in the step 2 is performed, but with different distribution of iterations scheduled. Type, chunk size. The time spent on the third stage of gradient descent algorithm with different number of iterations and threads on a two-core processor with different distribution of iterations schedule, type, chunk size, are given in Table 3. Table 3. The results of parallelization of the third stage using a two-core processor. We can conclude that on average the parallel algorithm works much faster with different iteration distributions. Similarly, the execution time when tested on a 6-core processor. Figure 3. Visualization of execution time at parallelization of the third stage, 6-core processor. The parallelization algorithm of stochastic gradient descent is also performed in the work. The parallelization of this algorithm can occur by blocking the change of coefficients by each process, but this approach obviously does not allow to obtain significant advantages. However, there is an interesting Hawk-Wild algorithm, which allows you to change the coefficients without synchronization. This method works without any negative impact on the mathematical efficiency of the algorithm. The description of the algorithm is as follows. Each thread draws a random example I from the training data. Thread reads current state of data. Thread updates. The sample size is large enough, in this case 500,000, then one iteration is enough. Execution time for testing on 6 cores is given in Table 4 and Table 5, and data visualization in Figure 4. Table 4. The time spent on performing a stochastic gradient descent at different numbers of threads. Table 5. Efficiency and acceleration when tested on a 6-core processor. Figure 4. Visualization of execution time at parallelization of stochastic gradient descent 6-core processor. We present the results of parallelization of the gradient descent algorithm and stochastic gradient descent using MPI technology. Parallelization of the gradient descent algorithm. Execution time for testing on a 6-core processor is given in Table 6 and Table 7, and visualization of result on Figure 5 and Figure 6. Table 6. Time spent performing the gradient descent algorithm using MPI technology. 6-core processor. Table 7. Efficiency and acceleration are based on MPI technology. 6-core processor. Figure 5. Runtime visualization based on MPI technology. 6-core processor. Figure 6. Acceleration is based on MPI technology. 6-core processor. Parallelization of the stochastic gradient descent algorithm. The parallelization occurs by the fact that the rows of the matrix Xi are distributed between the threads. Each thread searches for a local model, then sends the found model to the main thread, where all local models are averaged, and we get a global model. The disadvantage of this method is that it requires additional calculations to find the model. Execution time for testing on 6-core processor is given in Table 8 and Table 9, and visualization of results at Figure 7. Table 8. Time spent performing the stochastic gradient descent algorithm using MPI technology. 6-core processor. Table 9. Efficiency and acceleration are based on MPI technology 6-core processor. Figure 7. Visualization of the execution time of parallel stochastic gradient descent algorithm based on MPI technology 6-core processor. The following are the results of parallelization of the gradient descent algorithm and stochastic gradient descent based on a hybrid of MPI and OpenMP technology. Table 10. The time spent on performing the parallel algorithm of the gradient descent method. Execution time, when tested on a two-core processor using hybrid technology for parallelization of the method of stochastic gradient descent, is given in Table 11. Table 11. Time spent performing the parallel algorithm of the stochastic gradient descent method. Conclusions. In this work, to optimize the regression analysis, the method of gradient descent and stochastic gradient descent based on OpenMP and MPI technologies are paralleled. Without reducing the generality, a number of numerical experiments were performed on one network date, on the basis of which the efficiency of the proposed approach is analyzed in detail. Acceleration was achieved 3 times when parallelizing the algorithm and gradient descent using OpenMP for 2 consecutive cycles with number of threads 2 and 4 on a 6-core processor. The problem of erroneous exchange is considered, which often has a negative effect on acceleration during parallelization using OpenMP. Acceleration can be achieved twice with different distribution of iteration static, dynamic, guided, and chunk size. The Hawk-Wild algorithm was an interesting discovery and its application to parallelize the task.